Gonna hit. Okay, so and then so the 40 hours online, then these Zoom sessions also count towards that, and they're here if you have questions as you're moving forward. In the early stages of the class, there are oftentimes very few questions because the early portion of the course is fairly basic, and and so it doesn't usually cause people to freak out. When you get into chapter 7, that's when people start to freak out. That's when they start doing the math and going, oh my God, how do I do this? This is all complicated. At which point I have to say, all right, don't worry about it. It's not that complicated. There are a lot of steps, but none of the steps are hard. Then of course you've got to do the online course, then you've got to do the hands on that we do in class in person, meet all of the hands-on requirements of the ETA certification, and then the exam. So you need to get a 75% on the exam. It's a simple pass fail. So if you get 100%, it's the same as if you got 76% as far as ETA is concerned. um, Rarely, I've only had two students in the whole history of me doing this that have gotten 100%. They were very different people. One was a young woman who had just retired from the military or had left the military. So she was in her like late 20s. And another was a monk. So take that for what you want. I, I was teasing him. I said, you cheated. You had someone helping you. So that was so
So,
anyway, but
can I ask a question, or do you want me to wait till the end?
no, 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 go ahead, jump in.
Um, so when I'm taking the exams, a lot of times you learn a lot by, taking the exams after the chapters.
Uh-huh.
And then you review it, and then, the ones you miss, I go back. It's kind of like with your online course. Are there answers for the exams on the textbooks?
Not
From what?
in the textbook, but the same questions actually are in the online course, the end of the
Okay.
chapter,
Okay.
and the answers come up online.
Right.
If you want the answers, I can email them to you. The reason I don't include them in the textbook, I used to, but then a lot of the teachers who use these in classrooms were complaining because they wanted to use the tests in class, as okay, I'm
Or
going
a
to
grade or something.
grade
Yeah.
and so if I gave them the answer in the book, then it was like getting a teacher's edition. So I have a sheet that I can send to you and say, okay, the answers for every question at the end of each chapter is this.
That'd
um,
be awesome because I go back and forth with the answers to study because I find that helpful.
yeah, and one of the things that I will say is if you can answer all the questions at the end of each chapter, you'll do fine on the certification exam.
Yeah.
The questions are very similar. I would say my questions in the book are a little bit more difficult because intentionally I give you the occasional question that I'm trying to be tricky or a little bit confusing.
Yeah.
Um, like I'll throw in a thing about it should be 10 feet away instead of 10 feet close, 10 feet within 10 feet, or it should be at least 10 feet. And you got to read them carefully.
Yeah.
Um,
Well, I
and
noticed that.
yeah,
Yeah.
and and I
That's awesome,
also
though,
I
because it
also
makes
do
you think.
I do a lot of negative questions. So which of the following is not?
Yeah.
Um, I like that because it gives me the opportunity to tell you three of them that are.
Yeah.
So I think it's a good teaching technique, but it can be difficult. It can be confusing when you take it because sometimes people's brains just sort of drift over the knot and they don't see it. So the exam will always try and do it in the positive, the certification, like which of the following is, but my questions will not. So um
No, that's good.
yeah. Yeah, so
Yeah.
if you
What I
can
do is I take I take the test, and then I see which ones because then sometimes what I do is I take the ones that are real confusing. I make note cards with them,
yeah.
and then I that's how I do. I do note cards, and just if I'm sitting somewhere having coffee, I go through them. So.
Well, there's also a tool online called Quizlet. If you go into the course here, let me just share my screen. And if I go in, let's find, is this the right page? Let me, can you guys see? I don't know that I'm sharing the right screen. Oh, let's try sharing this screen. Do you guys see my screen here with all the icons on it?
Yes.
Yep.
Okay, so if I jump in here, whoops, gonna jump that over. You guys can just see how discombobulated I am. All right, so if I jump here and if I go into our solarpvtraining.com website, uh, what I want to show you is I think you'll find it very, very helpful for studying if I can get into it.
No, that's awesome.
I always worry when I'm working here, I end up with 75 different screens open. And
That's that's what I do.
yeah, well, it's funny because when they first started allowing for this, for doing two things at a time, I remember asking myself, why on earth would anyone need to do more than one thing at a time? You know,
Yeah.
just shows how far we've come. So, okay, so if you're on the online course and you guys should have access, hopefully this page here doesn't look
Yeah. That's
it looks
it.
familiar, and
Yeah.
you can jump in here. But if you look over here on the right,
Yeah.
it says Quizlet. There's the ninth edition and the eighth edition. It depends on which one you want to study. But let's say we go into the ninth edition here, and the questions and the structure is a little bit different. But here we'll say this is the ninth edition. It will bring up chapter one, chapter two, chapter three. So let's say that you want to study chapter three. You can go in here and you have different formats. So you can set it up as a flashcard format.
Oh, cool.
And these are the questions. The PV system that uses batteries and is not connected. And you just click on it and it flips over and it's called, an off-grid system.
No, that's awesome.
So these things already exist as
Oh,
flash.
wow. That is awesome.
So then the other thing you can do is you can go in and you can say, okay, I don't want to do it as a flashcard. I want to do it like it's a test.
Oh,
And
really
here you
cool.
walk through and it'll give you the four answers.
Oh, that is awesome.
So you
So
can,
can I do it on my phone?
sure, yeah, yeah, you could just log in. And all you need to do, because the best way of getting into it is just to go into the solarpvtraining.com website and
Yeah.
just click on that link. And you can do that
Okay.
on your phone. You can do the online course on your phone as well. It will still work on your phone.
Cool.
Um, but this will let you do it as a test. There are also some other options here if you want to play around with it. You can do them as games. Like here's one that'll
Oh,
match.
really?
So you can
That's
start the
cool.
game, and now it's saying, okay, it picked a few questions, and it says you match the question with the answer. So it says PV system that uses batteries and is not connected. All right, that's going to be it's not connected, so it's going to be
Oh,
an
wow.
off-grid system.
Oh, that I like that even better.
Yeah, if you get it right, it pops it off. And there are some other ones as well. So
Okay.
so the Quizlet is a nice handy little preparation tool. And I've got it all set up there and away you go. So you don't even have to waste pieces of paper.
Hey, do you have an app?
The Quizlet app is free. Um,
So I can just press on it
yeah, you should be able to get
on my
that
phone?
on your phone. Yeah, you should.
Download the app?
Yeah, and it's free for students and it costs me money to post things there. So that's the way
Okay.
they work. So I've already paid the fee. You should be able to go in and just access the course.
Okay.
Um, So if you upload the app on your phone and then just search for understanding photovoltaics, it should take you into these courses.
Oh, that is awesome. So it's an app too. That's amazing. I didn't know that.
Yeah,
Okay.
it's also, I'm just not that good with my phone. I like to just live on my computer rather than my phone. Um, so I'm not really that familiar with it. I can't tell you, but I'm pretty sure that's the way it works.
Yeah, I'm just when I'm just in between meetings or something, I can do it. That's
Yeah,
awesome.
sure. Uh-huh. Okay, so speaking of chapters, well, we're basically, I think chapter 4 and chapter 5, is that right? Is that about where we should be
Yeah.
at this point? So I wanted to touch base and see, let me review real quick the IV curve issue. So I'm gonna go ahead and pick one of these screens. Let's try that and see. You guys are going to see all my emails here, right? Get rid of that. Get rid of that one. Oops, I don't want to do that. I almost canceled. Screen sharing has stopped. Okay, so I clicked on wrong things. All right, I'm going to go into, yeah, this one will take me and work over on that other screen. You guys should see the Quizlet screen here in a second, or is that what you're saying?
Yeah.
Yeah, I found with this the best thing is to just go into Paint and treat Paint as a whiteboard. All right, so I want to talk about the IV curve. Whoops. So, whoops, I need to actually pick that. So if we talk about an IV curve, if this is amps and this is volts, let me see if I can use my pencil. It keeps wanting me to, no, that's only working on that screen. All right. So the IV curve of a standard solar panel is always going to look something like that. This
Uh,
being amps,
Jay, you're showing the wrong screen.
Yeah.
I did you mean to show the paint screen because we're not seeing that.
which screen?
I see a
Or we
screen.
don't see it.
Does that help?
We can't see the IV
Not yet.
curve.
Oh, you can't see it at all, huh?
No.
All right, let's try it again. Um, Here we go. Try that. Does that show you the IV curve?
Ah, yes.
All right. Okay, let me, because I've got it on my right screen here. So if oh, I thought I could just erase the whole thing. I was using my, come on. There we go. Technology. Ain't it wonderful? All right. So if I do an IV curve, so here's my amps, here's my volts, and typically you see the IV curve looking something like that. And the points on this curve that we need to worry about, the maximum amps is referred to as the ISC. The maximum volts is the VOC. Now, these are typically theoretical maximums, especially the ISC is a theoretical maximum because anything times zero is going to be zero. So when you talk about how many watts it's generating, that's what this curve is. Amp watts equals amps times volts. So when we multiply that, we get a curve that looks like this. Well, at ISC, there's 0 volts, so there's 0 watts. So it is a
Okay.
theoretical maximum because current essentially requires a load. Otherwise, there's no flow. So it's going to be 0. Now, as soon as you get off of that line, then it no longer is theoretical. Now it's real, but it's just a fraction off the 0. But ISC is the theoretical maximum amps a panel could generate under standard test conditions. So this is a single instant curve. So what do we mean by standard test conditions? We mean 3 conditions basically are present. The first is irradiance. So what's the irradiance at STC?
1,000?
1,000 watts per square meter, right? What's the temperature?
25?
Yeah, 25 degrees Celsius. And then air mass, which is 1.5 air mass. So we oftentimes refer to that as atmospheres, but it's not exactly right. It's basically saying that the waves of the sun have to travel through 1.5 times the thickness of the Earth's atmosphere in order to hit the ground. So it just means it's coming in at a bit of an angle. All that means is that it's basically northern hemisphere. Why did they come up with those STC terms? My understanding is it really didn't matter what they were as long as everybody was consistent. So when the guys were meeting, they were meeting in Paris and they said, we need to come up with a set of conditions that we will judge all solar panels against. They said, well, how about today? Right? Let's go outside. What's the temperature? What's the irradiance? And it turned out irradiance was about 1,000 watts per square meter. That's a clear day at sea level. In Paris, it's 1.5 atmospheres or 1.5 air mass. And it was 25 degrees Celsius, which is 77 degrees Fahrenheit. So what they're doing is they're saying, okay, when we test a panel, let's just use the same conditions so that I know that this 300-watt panel is the same as that one. It's not saying they're going to generate 300 watts. It's just saying that they're the same because conditions affect the panel. So you know that one 300-watt panel is going to be similar to another one. That's all STC is all about. What we find is those conditions are rarely met in reality. It's oftentimes colder than 77 degrees Fahrenheit or 25 degrees Celsius. If it's colder, the panel will generate more, and it's typically going to affect voltage. So if I've got a string here, and let's say it's not 25 degrees Celsius, but it's 0 degrees Celsius, this IV curve might look something more like this.
Oh, okay.
So it's going to have higher voltage. It affects the amp somewhat, but not that much.
Hmm.
So now if we're looking for the maximum power point, well, at STC, the maximum power point, which is the point along that curve where the most power is produced, is right there. And there is a voltage associated with that point, which is right here, which we
Okay.
call the VMP or the Vmax, which is the voltage at the maximum power point. It's not the maximum voltage. It's the voltage when
Okay.
the panel is generating the most power. That's
Okay.
confusing because VOC is the maximum voltage, but VMP or Vmax is not. It's just when it's producing its most power. And the amps that are associated with that point, that's the Imax or the IMP. They haven't standardized on terms. So it could be the amps at the maximum power point or Imax. These should be the points or the numbers where the panel is actually functioning. These are the theoretical maximums. And these numbers move around when conditions change. So for instance, when it gets colder, that maximum power point might be over here. And so the Imax goes up, the VMP goes up. So all those numbers are changing. Well, that would be hard to deal with, except that there's a device called the MPPT the maximum power point tracking device. And it's located in the very first piece of electronics that connects to the solar panel. So it might be a microinverter, it might be a power optimizer, it might be an inverter, it might be a charge controller. Each of those, whatever thing is connecting to the panel first, there is a maximum power point tracking device, and it makes sure your panel is operating at the maximum power point as conditions change. So you don't have to think about it as an installer. It's just going to happen automatically. So that's nice, but it keeps changing the conditions under which the panel is operating. So we sort of take a snapshot when we're doing and we're going STC. That's the numbers that come with the panel specs, but they're rarely going to be operating at those numbers. That's just a snapshot. I know, Michael, you're a lawyer. That's the way the law operates, right? They take a snapshot of the world and then they look at it under those conditions, even
Uh-huh.
if conditions have changed. So, so that's what we're doing here. We're taking a snapshot, and that's what we deal with. Um, okay, so you understand that relationship?
No,
Everybody fine?
yeah, it's pretty. Yeah, I do. After reading it, it's really difficult, but this actually is does a really good job of understanding.
Okay, great. And what we're worrying about, why do we care about ISC? Why do we care about VOC? Well,
Yeah.
we use those when we're designing the system. So when we size wire, wire is very dependent on amps. If you
Mhm.
exceed the capacity of the wire can burst into flames, it can burn up. Wire has a limitation of how many amps it can handle. So my design is going to be based on the worst case scenario of the amps that are going to come through this. So I'm going to use ISC as my starting point for my wire
So
design.
to determine the size of the gauge of the wire, yeah,
Yes,
and
yeah.
the length of the wire too, right?
Well, the length of the wire is more going to be a matter of just designing the system. How far is it going to be from this
Right.
point to that point? But the size of the wire, that's going to be based on the amount of amps that are going to be going through the system. There are a few things that we derate. Now, the NEC says, all right, once you've decided on that, then on how many amps are going to come through, and we get that from ISC, we want you to multiply that times 1.25. That's the NEC safety margin,
Okay.
because they always want the wire to be bigger than what you think you need. So this is true in every bit of electricity. If you design a kitchen outlet, if you think that you're going to run 20 amps through it, you've got to have wire there that's capable of handling 20 amps times 1.25. So that would be what, 25 amps? So you'd have to have 25 amp wire to handle 20 amps. It's just a margin of safety. Now, with solar, they come back and they say, now I want you to multiply it times a second 1.25 safety margin. So this is the NEC, that's on all wire. Now, this is the solar safety margin. So we would have to then multiply it times 1.25 times 1.25. And the reason for that is irradiance is what really affects amps. And remember, this number is based on STC, which assumes 1,000 watts per square meter. But at the outside edge of the Earth's atmosphere, it's actually getting somewhere around 1,300 watts per square meter. And I've taken measurements on a clear winter's day where I've gotten 1,200 watts measured at the ground. So STC assumes 1,000, but it could be as much as 1,200, maybe even 1,250. I've never gotten that measurement, but it's possible. So they're saying, okay, because irradiance can be bigger than what was assumed to come up with this number, multiply it a second time by 1.25 just for that added safety. Now you could say, well, why don't we just take ISC times 1.56 if you're really good at math, which is 1.25 times 1.25, And that would work too, except electricians are not that smart. So they just simply they know to do the 1.25. They do it on everything. So then you say, okay, do it again. Do it again for solar. So that's why we teach it that way. So we do it 1.25 times 1.25. Now, this only has to happen until that device connects to the first electronic device, or that circuit connects to the first electronic device that controls the signal. So usually in a straight grid tied system with a string inverter, the string inverter is going to be that first device. So all the wire leading up to the string inverter is going to be basically wild voltage or wild amperage. It's going to be varying depending on sunlight variations and temperature variations. Once we hit a piece of electronics, that typically then gets controlled. So in a standalone system, the first piece of electronics is usually going to be the charge controller. But if you're using power optimizers or you're using microinverters, basically those are going to control it straight from the panel. So that second one goes away because the optimizer or the microinverter is now managing the output of that device. So we don't have those fluctuations based on irradiance. We still use the 1.25 NEC safety measure, but we no longer then have to worry about the variation in solar. So hopefully that doesn't confuse you more, but
So if you have a microinverter on each panel, you don't really have to worry about this as much then.
right, exactly.
Yeah.
Normally what we do, let me clear this screen.
Or if you just have, so you can have a master microinverter, right? That controls like four panels.
They do make microinverters that control multiple panels.
Yeah.
But one of the advantages of microinverters is that MPPT is located, each panel operates individually.
Yeah.
So if one of the panels is shaded, it only affects one panel.
Okay.
In a string, when you have a string of panels, let's say here, I've got, let's say I've got 4 panels connected in a string, and then that string goes through a junction box, and then let's say it comes straight to my inverter. Typically, the symbol for inverter is almost like a diving sign, half DC, half AC.
Mhm.
Okay, so let's say that each of these panels is designed to generate 300 watts. So that one's generating 300 watts. This one is slightly shaded here, and it's only generating 100 watts. This one's generating 300 watts. This one's generating 300 watts because they're all doing just fine. Well, if they're hooked up in a string, the output is going to be the lowest common denominator. So the whole output of that string is only going to be 400 watts, even though only one panel is affected by shading, it affects the entire string. So one of the reasons you like microinverters is now that MPPT is handled by that device on each panel. And now the output of that would actually be 1,000 watts because each one operates independently of the other. So that's a reason for using a microinverter or a power optimizer. An optimizer does everything that a microinverter does except convert the DC electricity to AC. It leaves that for a fixed voltage inverter back in your house, or in the basement or in the garage, wherever you happen to put it. The reason you might use an optimizer system versus a microinverter system is that they're cheaper. That's the main reason. Like each of these microinverters might cost you $160 for each one, where the optimizer might only cost $50. So but you still have to buy an inverter. But depending on the size of the system, this inverter is only going to cost you like $1,200. So if you've got more than 12 panels in your system, you may actually come out financially to go with the optimizer system versus the microinverters.
On
Um,
each one.
yeah,
Uh,
just financially.
yeah, Jay, I'm a little confused as how you got that 400 watts when the second panel was shaded.
Yeah.
These connected in these must be connected in series, no?
Yeah. If these are connected in series
Right,
and this one is shaded down to 100 watts output, I'm
right,
not getting into volts or amps yet. Well, then all of the panels connected in series are going to operate at the lowest common denominator. So this one will no longer generate 300 watts. It's only going to generate 100. And that one's only going to generate 100.
right.
That
I
one's going to be
understand.
100.
I understand that. I just wondered how you got 400.
Because there are four of them in series. So they're each going to be operating, they're each going to be
Ah,
producing 100 watts.
got it,
So you're
got it,
going to get 400 watts at the end. But that's
got
a significant difference between the 400 watts and the 1,000 watts for the same amount of shading,
right.
so that becomes a big issue. Um, so if we look at the typical configuration here, when we talk about a grid tied system, when we're talking about the various devices, typically you're going to have a solar array that's up here for a grid tied system. Then we're going to go to either a junction box or a combiner box. What this is a cable transitioning place. The wires that are coming off of the solar panels, they're going to be MC4 PV wires, and they go and they're terminated into this box. And from here, we're going to go with cheaper wire in conduit over a longer distance. So we need a place to transition. The only difference between a combiner box and a junction box is in a combiner box, those strings that come in, let's say there are 3 strings coming in here. So three strings from your solar array, and a string is panels hooked up in series. Well, in a combiner box, you would combine those strings in parallel and leave with just one set of wires, one positive, one negative. It'd be a bigger wire because the amps would increase, because when you connect in parallel, amps increase, but voltage stays the same. But it would be just one string. So this is what I'm drawing as a one-line diagram. So this would be a traditional system where we go in and we do a combining. And then from here, with one string, we end up going to a DC disconnect. So this is very common. We would go from the combiner box to a DC disconnect. Now, in the world today, that DC disconnect is typically integrated with our inverter. It doesn't have to be, but there usually are.
Mm.
Um, so it may be physically just already pre-wired, so you don't even have to worry about connecting from the DC disconnect to the inverter because it's just already there. But it might not be. From the inverter, we then go to an AC disconnect because now we're in the world of AC, right? The inverter has changed the DC signal from the panels to AC that we can use in our loads. That's kind of the whole reason we have an inverter. Now, some of the things around this AC and disconnect is it's got to be externally operable. It's got to be labeled. It's got to be lockable. So you've got to be able to lock it. You don't have to put a lock on it, but you have to be able to lock it. And it's got to be located within 10 feet of your meter, your electrical meter. And the reason for that is this is considered the main shutoff of your array. And when they come, if a first responder or if the utility wants to turn off the electricity to your home, they typically go to the meter. And let's say your house is on fire, the first responders are going to come and they're going to pull the meter. Now they assume there's no electricity in the building. But there will be a label on that meter that says, wait a second, there's a second energy source. It's a solar array. Could be a generator, but in this case, it's a solar array. So they look around. Well, that disconnect's got to be within 10 feet of where they're standing. So then they go over and they turn off this electric meter. So it's got to be external operable. They don't want you to have to get a screwdriver out and open it up. It's got to have that little disconnect switch there, but located within 10 feet of that meter. Now, from the AC disconnect, we typically go into the service panel for a load side connection. We're going to just hook into a double pole breaker. And then from here, we've got the main, and the main's going to go out there to the meter. So that's a typical grid tied, basic, good old fashioned string inverter system. So any questions about that?
No.
Okay, so this is the way up until say 2014, pretty much every system we ever designed looked exactly like this. So up until about 10 years ago, that was the norm. Then they passed the NEC added a provision they called the rapid shutdown rule. And the reason for the rapid shutdown rule was the situation like here's your house, and on the roof, you've got a solar array. Okay. Now your combiner box, typically located under the solar array so that you don't see it. And then you drill through the roof and you take your wires in conduit through the attic. Let's say we decided we're going to just run it up here and it's right on the underside of the deck and it comes. And then we poke through the outside and we come down here, the side of the building in conduit, and we go to our DC disconnect. Then from here, we go back into the building, and I'm going to draw some grass here because I want to put this in the basement. And in here, we've got our inverter in the basement. Then we have to go back outside. This is all a little bit cumbersome. And we go to our AC disconnect, which is located within 10 feet of the meter. And then from the AC disconnect, we go back inside and we connect into our service panel. Again, up until 10 years ago, this is the normal way you did it. And it was a little bit cumbersome because we had to go back outside to put the AC disconnect there. But that's because the first responders have to be able to turn off the system. Everybody follow me so far?
Mm-hmm.
All right. So now on this house, this poor unfortunate house, it bursts into flames. Woo-hoo. Middle of the afternoon. House is on fire. The firemen come, and the first thing they do is pull the electric meter. All right? So that there's no electricity in the house because they don't want to get shocked. They see the label and they say, oh, there's a solar array on this house. We need to turn it off. So they turn off the AC disconnect. Now the system is shut down. Well, how does it know to shut down? Well, as soon as the inverter loses sight of the grid, because of anti-islanding, it turns off in the inverter. That's the way these things shut down. So the shutdown is taking place in the inverter. Problem is, all this wire going from here down through here and all the way to the inverter, that's live. That could be 600 volts DC, even though the system is not generating. So then a fireman climbs up on the roof with his chainsaw. He cuts through this wire and he dies because he just got electrocuted. So he's cutting through it to vent the roof, because there's smoke building up or whatever. So the NEC came in and they said, all right, when you turn off this disconnect, we want the power to shut down at the array, not at the inverter, because we don't want these guys cutting through any live wires. So they did this in 2014. And at the time, because I was teaching solar at that time, the industry basically said, how do we do that? And the NEC said, we don't care. Make it so, and if you can't make it so, you don't install, because they don't care how much your system costs. They don't even care if it works. They just want it to be safe. So that was their marching orders. So some bright guy got the idea, oh, you know what? We could just move the inverter right up next to the array. Well, that works on a flat roof. If you're doing it on, a Walmart or an Amazon, you could put the inverters right up next to the solar array. But it doesn't work on a traditional shingle house, putting a 100-pound piece of equipment up on the shingles right next to a solar array. First off, it looks like hell, but it's not going to stay. It's no good deal. So then Enphase said, I know what we could do. We don't have to put a big inverter up on the roof. Why don't we make a whole bunch of little inverters and attach each one to the solar panels, so that every panel has its own little mini or micro inverter? And that's the birth of the microinverter world. And the byproduct of that is every panel behaves independently of every other panel. So you get MPPT tracking, you can monitor the performance of every single panel so that you know what each one is doing. When one panel goes bad or one inverter goes bad, the communication system can let you know. So there turned out to be a lot of benefits of that. But then SolarEdge said, you know what? You don't have to put the inverter up there. Just put all the other electronic stuff up there, because we can do that a lot cheaper. And so that's where the optimizer, the solar optimizer industry. So SolarEdge said, well, let's put the electronics up there, but let's keep the inverter down in the basement. So now when you turn it off, the anti-islanding is up there on the array. So it shuts off at the array. Everybody's happy. So that's why we have optimizers and microinverters. And right now, microinverters represent about 60% of the residential industry, and power optimizers represent about 30%. So this industry that didn't exist 10 years ago now dominates because it's really good. Now, even if you have a string inverter, if it's on a building, it's still got to have a piece of electronics on every panel because of what's referred to as rapid shutdown. So if it's on a building, there must be a piece of electronics attached to the solar panel. But if it's ground mounted, it doesn't have to be there. So that other 10% may be string inverters that are on the ground, or it may be string inverters that have another electronic device up here. That's not an optimizer. It's not a microinverter. It just has the rapid shutdown built into it. Might have an MPPT built into it. It might have communications built into it, but it has the rapid shutdown built in. Does that all make sense? Okay. I think we're pushing right up. That's a good stopping point for this. We'll talk a little bit more about it when we meet next week. I think we can, if you run into any other questions on chapter 5, I think rapid shutdown comes up in chapter 5. Chapter 4 was basic electronics or basic electrical. So there's not a whole lot you need to know about basic electricity except watts equals amps times volts. Oh, remind me. Yeah, we'll do voltage drop equations because voltage drop equations might be something that's new to you. Essentially, the three things you need to memorize, the three equations. I'll jump back into my paint here. Is so I can write them down. The three equations that you need. First is the power equation, and it's very basic. It means watts equals amps times volts. Hopefully that's somewhat familiar to everybody. Watts equals amps times volts. You may see it expressed as P equals I times E. They always say electricians like pi. It's the same, it's the same equation. Power equals amps. And in this case, they've talked about E as electromotive force instead of volts. Again, same term, same issue. So we usually use watts equals amps times volts. Then the second equation is Ohm's law, which is volts equals amps times resistance, or Ver. And all that is the it just shows that those things are interrelated. The best analogy for this is to say watts is like, they use the water analogy. Watts is the amount of water flowing through a pipe. Amps is the size of the pipe, and volts is the water pressure. So how much water flows through that pipe is a factor of either the size of the pipe or the pressure it's under, or a combination of the two. You increase the size of the pipe, you're going to get more water. Increase the pressure, you're going to get more water. And if you do both, you're going to get even more water. Well, volts equals amps times resistance, that's Ohm's law, basically says, think of resistance as the friction that the side of the pipe puts on the flow of the water. So the bigger the pipe, the less the friction. But over a distance, the water slows down a little bit because it rubs up against the side of the pipe. Well, resistance is similar to that. Over distance, you lose some of the voltage, which is the pressure. The pipe size doesn't change, it stays the same, but the pressure is decreased over distance because of voltage. It's referred to as voltage drop, but it's resistance that causes voltage drop. Everybody clear on that? And then the third equation, and hopefully you'll just practice these, is voltage drop. It's the voltage drop equation equals amps, and it's usually the operating amps, amps at MP or amps at Imax, times resistance, times twice the distance over 1,000 feet. Well, why do we, all this is Ohm's law adjusted for distance. Well, why do we adjust it for distance? It's because the resistance of the wire that we're given in the table is its resistance per 1,000 feet. So we just need to know what fraction of 1,000 feet we're talking about. So the NEC puts it in ohms per 1,000 feet. How many feet? Well, and why is it twice the distance? It's because it's a circuit. It goes there and it comes back. So if I'm running at 200 feet, I'm actually running 400 feet of wire, there and back. So that's twice the distance of the run divided by 1,000. So in a case like this, if I've got an IMP of, let's say, 8.5 amps, and we're using number 10 stranded copper, which is 1.24 ohms per 1,000 feet, and it's going, let's just say 350 feet. Well, that'd be times 2 divided by 1,000, or just 0.7. So we would take 8.5 times 1.24 times 0.7. I'll bring it up on my little calculator here. And somebody may be faster than me, but 8.5 times 1.24 times zero point 0.7 equals 7.378, or basically 7.4 volts. What that's saying is we just lost 7.4 volts taking that much amperage on that size wire that distance. So we lost almost 7.5 volts. Well, is that a problem? Well, now it depends. It depends on the situation. If it's a 12-volt circuit, it's a big problem because you just lost like 3/4 of all your power. So at the end of that run, you're only going to have what, 4.6 volts because you just lost it. But if it's a 600-volt system, well, you only lost about 1%, a little bit more than 1% of your power. So it's not a big problem. So this is the reason in the electrical grid, if you've got a power plant, typically the power that leaves that coal burning power plant or that natural gas power plant is leaving there at like 700,000 volts. And now it's going to go and it's going to go through those big wires, those big towers that you see when you drive along the highway sometime. I always think those towers look like a cat or something. They've got little ears on them sometimes or whatever. Very high up, high tension transmission lines. The power is flowing there at 700,000 volts because it's losing voltage for every mile it travels. But if you start with a really big number, the amount that's lost is minor. Then you get to a substation, and it's usually stepped down from 700,000 down to about 7,000 volts. So that power is then going through your city, and all those power lines you see out on the road are going to be like 7,000 volts. Again, it's traveling a distance, it's losing voltage, but not that much comparatively. Then it gets to that little can that's up there on the pole that's feeding your house, and it gets stepped down again to 240 volts. And that's what's feeding your house, 240 volts. Well, if it started out at 240 volts, you wouldn't get any power by the time it got to your house. You'd have lost that much. So that's just the way our grid operates. That's why we use AC electricity instead of DC. It's because back when the grid was being formed, DC electricity had no way to step up or step down the voltages. AC electricity could use transformers, and those transformers could make the electricity higher voltage or lower voltage. So I always tell people the reason we use AC instead of DC is because Tesla was smarter than Edison. You know, now in today's market, you can step up and down DC electricity. So there's no reason to continue with AC electricity except that that's what we do. You know, why do we do things the way we do it? It's because that's the way we do it. You know, why do we drive on one side of the road, not the other? It's because we do. You know, there's no inherent better side of the road to drive on. We just drive there because we do. And the British drive on the other side because they do, you know, and it's too much of a hassle to change. That's really kind of where we're at. So, all right. So I went a little bit over, but hopefully, as you're studying, if you have any questions, you know, store them up or send me an email or give me a call, and we'll try and keep you on track because I don't want you to get lost as you're studying. You know, I want you to keep flowing along, understand what you're doing. If you come to a thing and you're lost, that's just going to make the next step harder. So let's make sure you stay on track.
Jay, this
Yes.
is Nigel Tudor. I had several questions for you.
Okay. Fire away.
First out, you said that a lot of the newer inverters use the smartphone for the readout.
Yes.
Can you buy an auxiliary readout for some of the inverters? Because if you're talking 25 to 30 year life, if you think back 25 to 30 years, you know, where we've come, you know, in 10 or 15 years, your smartphone probably is not going to talk to the inverter any longer.
Yeah. No, Normally not. It's a problem. We ran into even another problem about, you're saying the technology may become superseded, and hopefully they'll make them forwardly compatible, but they don't always. Is N or not Enphase, but Solar Edge. Actually, they used to have little meters on their inverters, a little LED screen that you could look at that. And it was a redundancy. Well, they did away with them, saying that you could then just look at your phone. But in some rural installations, there's no cell service. So you cannot install their system because you can't use your phone. It requires the phone to install it. That very problematic. Um, the problem is these things are developed and manufactured in Southern California where they cannot imagine somebody doesn't have broadband service. They also can't imagine a thing such as snow. So sometimes these things don't operate, if it's below freezing, and you're like, seriously, guys? Yeah, but they just think, okay, well then why don't you move someplace civilized? It's like that that's that's a problem. Okay, so I don't think I got a solution for you there.
So my next question was on the batteries. You were talking the lithium ion if they're damaged and they can burst in the fire. But does the lithium iron phosphate batteries, are they still considered lithium ion batteries or not?
Yes, yes. There are
Okay.
several flavors of lithium ion batteries. There's lithium iron phosphate. There's some other ones. Some are less subject to that. They call it thermal runaway. And I don't remember which is which, but like for instance, the N phase, it might be the lithium iron phosphate is less prone to thermal runaway than the other one, the two most popular. The one that Tesla uses is typically the ones that burst into flames. The ones that Enphase uses are not. So I'd have to look it up. But
And do both microinverters and power optimizers monitor individual panels or not?
typically they do.
Okay.
Yeah, they have individual communication devices, and you can even buy them for string inverters. Tygo, a company called Tygo, will they produce these for some of the best selling string inverters. So even if the string inverter is not individually monitoring it, you can get a device that will.
And then I had another question about the six handle rule.
Uh-huh.
So the where our meter is, we have a farm and we have many buildings. There's multiple disconnects for each building. Um, and if we add some more buildings and we put disconnects for solar, we would get over six handles.
Yeah.
So is there a way that you should do it so that you stay under six handles? Or
Technically, yes, there's a device called a disconnect aggregator. So it's basically one disconnect lever that will turn off multiple things. So you could just simply feed your lines, your disconnect lines into that one unit. My guess is in a rural environment like that, why do you have so many handles? Do you have generators and do you have wind and things like that?
no, we have the it's outside where the meter is. It's just a frame and the meter's there, and then there's individual disconnects for every building.
Okay. Yeah, you might want to put a master disconnect in,
Okay.
and then feed everything off that master disconnect. That would deal with it.
Okay. Because
It-
just, reading about that, I'm thinking, oh, that's going to be a problem.
Yeah, it might be. And my guess is your guys, your inspectors, even if you have an inspector, some rural communities don't have inspection at all. Like the county our farm is at, we have no electrical code. We have no inspector. Um, so you probably wouldn't run into problems. The only reason why it's limited to six is because they said so. We used to joke is say, why is it six? And it says, well, seven's too many and five isn't enough. That's literally how they came up with this. Apparently, is at one of their meetings back in the 1930s, there was a big argument about how many disconnects, and one guy wanted 10 and one guy wanted 2, and they ended up compromising at 6. That's that, and we live with it ever since. Apparently, it used to be a big problem in the early days of electricity because you might have a 20 amp circuit coming into your house, just 20 amps. That's plenty for your lighting and whatever else you might do. Then you buy a refrigerator. Well, now you need more electricity. So they just installed another meter that serviced just your refrigerator. And then you buy an electric stove and they installed another meter that serviced your electric stove. And so, like every appliance you added got you another meter. And so there were multiple disconnects. And they just finally decided this is getting crazy. We need to put a limit on the number of disconnects. And so that's where it came up. So, but I would say put in a master disconnect.
Okay, and then I have one last question.
Sure thing.
Is on your voltage drop equation, for three phase, you added in a times 1.73.
Yeah.
And I realize this is an odd question, but is that the same when you're talking 208 three phase versus 240 three phase? Because usually the square root of 3 is going to be like 208, where you're talking about a Y, versus 240, where you're talking about a delta service.
Yeah, my understanding is, yeah, the voltage drop isn't dependent on what configuration or what voltage you've got. But I don't want to pretend to be an expert on three phase. But I think it's just because the way the electricity runs through three phase, the voltage drop is going to be less, square root of 2, or but I don't think it's dependent on what configuration you have. But that's something that's good to know or good to be aware that it's slightly different, but you don't have to memorize it for this level certification. That's not going to be on a test. What I do is I introduce three phase only because you need to be aware of that there is a difference. But you're not going to, for the most part, be doing three phase installs. You might, if it's a commercial, if you've got a commercial property there, do you have like grain dryers and things like that?
We have machines that run on three phase. We
Yeah.
use phase converters to create the three phase at the different buildings.
Oh, okay. So you've got single phase coming into your home or into your farm, and
Yes,
then
yes. We actually have three phase on the pole, but because they want a demand meter where you get charged for your peak usage for.
Oh, yeah, 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 yeah. So you were going to be billed like a commercial.
Yeah, and the way we work is it's a rainy day, we'll go work in a workshop and use the machines,
Yeah.
and then you'll have 5 nice days, we'll be out in the field. It's not like we're there every day doing the same thing. So at least thus far, we've just used phase converters.
Yeah. Yeah. And what Nigel's talking about there is what they do on commercial properties is they have a thing on your billing called demand charges. And your bill is affected by the amount of energy you use during the peak load 15 minutes during the month. So if you had a big machine that used a lot of power and you only ran it for 15 minutes in a month, you might double your electric bill for the month just because you used a lot of power for a brief period of time. They don't usually bill that way on residential systems. So, but it can be a significant cost for commercial. So one of the things that we as the solar industry are doing is installing batteries to essentially load level so that you can take that big load, run it off the power that's stored in the battery, and then recharge that battery over a significantly longer period of time. And that's a good way to reduce your bill because you're essentially load leveling, or peak shaving, I guess is the right term. But all right, we get into that a little bit later in the book. So is that it, Nigel?
That's it for today.
All right. Well, that's good. I appreciate the questions you've been thinking. So, all right. Well, we'll definitely let you go now. and Michael can sit down in his car for the rest of the afternoon
Yeah,
and think about how good electricity is.
yeah, it is. I mean, that's why I'm thinking about solar on our roof because it happens about 3 times a year.
Yeah.
Yeah.
Well, definitely worthwhile. All
Thank you.
right. Talk to you guys later.
All right, see ya.
Bye bye.